Hello and welcome to another video of Intro to Machine Learning. This is lecture 21. In this video, we're talking about something known as regularization. There are two forms of regularization, ridge regression and lasso. We are going to talk about both of them, and finally we'll see a Python implementation. Okay, so what is this regularization? It is a technique for constraining or regularizing, that's where the name comes from, the size of the coefficients in a linear model. Just remember that we are talking about a linear model throughout, and one of the important aspects or issues of linear model is that of overfitting. So we are talking about that, right? So therefore, like shrinking them towards zero helps. We'll see how this technique helps. Okay, so it reduces model variance. If you remember our video on bias variance trade-off, you will remember that minimizing overfitting will let our model generalize well. So what does that mean? Okay, now if we have a highly complex model, for example, we have lots of features and we are trying to model that using a linear model, overfitting is one of the issues that might come up, and we want to deal with that, right? And one way of dealing with that is regularization, right? So what regularization does is that it adds a penalty term to the linear equation, or you can think of the objective function, which was the ordinary least squares that we calculated in a linear model. And based on that objective function, it tries to minimize the coefficients, and some of them tend or almost become zero, right? So if that is not super clear to you, just remember the term penalty or a value that's added to your objective function. We'll see what that means in a bit. Okay, so why do we use it? As I said, there is always a chance for overfitting in linear models, and that will lead to higher variance. And some of the common causes are some irrelevant features. As I said, if you are building a linear model for a problem that has a lot of features, and most likely some of them are irrelevant, so the model will create coefficients for each of those, right? And you don't need them. And then although these features are not having a huge impact on the response, but then still it is created. So you need to do something about them. The other issue that might come up is the correlated features. I don't know if you've heard about multicollinearity. If you haven't, that's fine. It means that you have more than one feature that is giving out the same information because those two or three variables are correlated. So that's what the issue of multicollinearity is. That means that if there are two or more features that are correlated to one another, they're not really giving us a lot of information about the data, right? And if you remember the ordinary least squares, the method that we use for linear models is based on the assumption of independence of features. So if there is correlation, we need to get rid of that. Okay, so moving on, how does this work? Like we've talked a lot about regularization. It helps us deal with overfitting. This is again a form of regression that constrains or regularizes, as I said, or shrinks. If this makes you feel better, shrinks the coefficient estimates towards zero, right? So this technique is essentially discouraging learning a more complex model to avoid the risk of overfitting. Okay, so how does that happen? If you remember, this is the equation of the linear model. So the coefficients, the intercept, and then these are the coefficients, and then the variables, right? So let's say this is the second coefficient, second variable, and so on. Let's say some pth variable and coefficient plus some noise error term. So this is what the linear model look like. Then we have a fitting procedure that involves a loss function called the residual sum squares. So we have to minimize the residual sum squares. We have to choose these betas such that we can minimize the residual sum squares. What was this residual sum squares? So this is like a review from something that we have seen before. Sum up for all the values of my data, right? My training data rather, and try to minimize this. So this is my response. This is the output value, right? Minus the intercept, minus the sum of all, like starting from 1 to p, all these betas essentially. So I'll just like go and add j is nothing but beta 1, beta 2, and so on, and x, I, j. So this is like my variable value, right? So we are trying to minimize this. So this is known as the residual sum squares. we find the coefficients using training data, and if there is noise in the data, the model won't generalize well. What does that mean? So I'll train this model, I'll minimize. So my objective function is to minimize my RSS, right? And this will work really well. It'll give me some values of beta 1, beta 2, and beta 0, of course, and so on. It'll give me the values of all the betas if I solve this problem using training data. But if this training data had a lot of noise, a lot of um, error here, what will happen is that when I use the test data, this will not generalize well. These values will not generalize well. They'll not do a good job of predicting the unknown values. And what will happen is that we'll have a model that does not have good prediction value or does not give good accuracy, right? So that's the whole idea. And that's when regularization comes in. It is going to regularize or shrink the learned estimates towards zero. So these are my learned estimates, right? And regularization will help me shrink them or at least bring them down, some of them, depending on which are the irrelevant features and which are not. And it actually uses a really intuitive idea, right? I explicitly go ahead and add a penalty term here, and that's going to help me reduce these estimates. How does that happen, right? Okay, so what happens is that a shrinkage quantity is attached. So let me write a shrinkage quantity, which is nothing but a function of those estimates itself. So I'll have the the residual sum squares already. So I'm trying to minimize this. But in addition to this, I'm also trying to minimize a penalty term, which is also a function of those estimates, right? So think about this as a budget that I will assign, right? And based on that budget, based on the value of the penalty term, I cannot go beyond certain values for my betas. And in fact, I try to minimize them because the overall objective function is to minimize this entire thing. So this penalty term will help me bring that down. So how does this look like? What is this equation and how does this look like? Even before we began looking at the equation, I just wanted to let you know that regularization has two types. So the first type is ridge regression that we are going to look at, and the second type is lasso, right? You might have come across these terms, but these are types of regularization. So let's look at what ridge regression looks like. So we just saw this equation, right? So this is nothing but RSS or residual sum squares, and this is my penalty. Now notice what penalty has. It has something known as lambda, and it has the sum of the squares of all my coefficients, right? So lambda is known as the tuning parameter because it decides how much to penalize the model, how much to penalize the flexibility of the model rather, right? So this is also known as the tuning parameter. This is my tuning parameter, and here is my final objective function, right? Now think about it. When lambda is 0, right, then it has no effect on the model, right? And when lambda tends to be very big, so almost reaching infinity, the impact of shrinkage penalty is growing, approaching a huge value. So then the betas will become really, really small, right? Approaching 0 because we are eventually trying to minimize this, right? And this is actually helping us take these betas and like towards 0 when lambda is huge, right? So how do we select this lambda? Selection of lambda is important in ridge regression, and it is done by cross validation. So we've covered cross validation in one of the earlier lectures, but it helps us determine the value of lambda. Now, the estimates that are produced by ridge regression or by this particular technique is also known as L2 norm. And you can tell that just by looking at the beta squares here, because this is nothing but the L2 norm. Right, so this is ridge regression. The second type of regularization is lasso. The only variation here is that it still has my residual sum squares. It still has the penalty term, but the penalty term is slightly different in the sense that this is now an L1 norm. So we are looking at not the squares of the coefficient estimates, but their absolute values. And then there again exists this tuning parameter that should be selected wisely, because based on that, we are essentially trying to minimize this entire equation, right? So now these can, like, if you're thinking about a two-dimensional space, this penalty term can be thought of as a separate constraint. So let's say I'm looking at a two-dimensional space where I have beta 1 and beta 2 only, right? So essentially, I'm trying to say that minimize my RSS, or residual sum squares, such that the sum of these, the coefficient estimates, is less than equal to some budget. And this budget is going to decide how much I'm giving, how much, like, what is the area of, like, this is going to be some kind of a square or a diamond, rather, right? So how much area is there of that diamond? And that's the budget, right? Similarly, for ridge regression, this equation for a two-dimensional space is beta 1 square plus beta 2 square less than equal to some budget, right? Depending on how much we are allowing this term to grow, right? So this is the constraint that gets added when we are trying to solve this problem. Okay, if this is not super clear, we can visualize this. So what's happening here in this picture, on the left-hand side is lasso, on the right-hand side is ridge regression. Now we just saw the constraint equation for ridge regression, which looked something like this, right? Less than some budget B. This is the equation of a circle, right? So that's that. This is the equation of a circle. Now these are the RSS, or the residual sum squares, because these are elliptical. Why? Because this is the equation of the ellipse, right? So that's why this is an elliptical equation, right? So these are the contours of RSS, because we're looking for different beta values such that we are trying to minimize these beta values in this two-dimensional space, right? So we are trying to maybe shrink, let's say in this case, beta 1 as small as possible. And until what value? It depends on the area of this circle, because that's what these are determining, right? So wherever we kind of intersect the two, that's the beta that we'll choose, right? So notice here, beta 1 is really, like, it's really close to 0, but it's not exactly 0. And this exactly 0 can be achieved by the lasso coefficients, just because it has this shape of a diamond, and it can achieve exact beta 1 equals 0 or exact beta 2 equals 0, right? Because this will have a point that lies on the axis, versus the circle might shrink to almost 0. But as you can see, the intersection can happen somewhere here. So that has shrunk the beta 1 value to a very small value, but that is not exactly 0. So that's why sometimes because lasso can make the coefficients exactly 0, it's also used for variable selection and yielding sparse models. So because here, as you can see, it will get rid of beta 1, right? In this case, it will shrink, like in ridge regression, it will shrink beta 1 to a very small value, almost 0, but it will not make it exactly 0. So that's the major difference, the central difference between lasso and ridge regression. It's the way the penalty term is handled. It's the way we are budgeting our constraint for beta 1 and beta 2, or for all the betas if there's a bigger feature space. Okay, so when to use which one? As I said, lasso regression is preferred if we believe many features are irrelevant and we just want to remove them, right? So if we want a sparse model, we don't want certain features, we need to use lasso. If performance is your concern, you should try both and see which one performs better. Elastic net search is another technique that's a combination of lasso regression and ridge regression. Okay, so that was about the idea of regularization. Let's go and look at the Python implementation. What I'm doing here is that I've taken up the same old problem of KC housing data. If you remember from the earlier videos, this is what the data looks like. And obviously we're trying to shrink some features and see the performance of the model. This data has a lot of features, as you can see. So obviously the ridge regression and lasso is going to get rid of some of them. So here what I'm doing, and I've provided the file, the code in the description below. Again, I'm importing libraries. All of this you've seen before. Data import. I'm getting rid of these ID, date, and zip code because this is not numeric data, and I'm trying to focus only on numeric data, right? And my output or my response is price, of course. So here I'm doing a train test split. the important thing that I want to focus on is that I have imported, along with linear regression, something called ridge and lasso, right? So these are the two models that come with the scikit-learn.linear model package. Here I've created the linear model. So let me actually run this part and create the linear model and try to find the score, which is the accuracy score on the test data, right? So that's all I'm doing here. And let's see the percentage of that, which is around 67.9. That's okay. Now this part is optional because here I'm checking different values of lambda. So if you remember, we said the value of lambda is critical, selection of lambda using cross validation. So that's what I'm doing here. This is optional. You might have simply created a ridge model equals the ridge class that we just imported here. And alpha is the lambda. So you could have tried a trial and error kind of a thing and used alpha the first time you're trying to create the ridge regression model. But here I've created a list of cross validation scores for the ridge regression model just using a loop, right? So every time I'm creating a ridge regression model and checking its score, right, for different values of alphas or for different values of lambdas, and then seeing which lambda should I use, right? So and then just like simply printing it out, right? So here, let's see. Yeah, so like if lambda was 0.25, this is the accuracy score and so on, right? Just look at like which one has the highest accuracy. For this data, it is not giving a ton of difference for different lambda values. So I just like went ahead and chose 2, and that's how I built my model here. So again, I used ridge class to create the instance of the class, and then it did a dot fit. So we've done that before, and as I said, with this data, we don't see a lot of difference in the accuracy. So this is 68. It is obviously gotten rid of or created estimates that are smaller than the original linear model, and so the accuracy is improved here, which is 68. A similar kind of technique I followed for lasso, where again I've tried to find which lambda works well by doing an input of different lambdas, just like we did earlier. And then again, this is optional. You can just directly go and create some values for your lambda and then create the model. So again, I found 2 was the best, although there isn't a lot of difference, and then created a model using that. So this kind of compares that lasso is not really giving a lot of improvement over ridge regression, so I'd rather choose ridge regression for this problem. That's it for regularization. See you in the next video. Thank you.